Hi everyone. Today I look at the relationship between pH, pOH, hydronium ion concentration, and hydroxide ion concentration. Something familiar to us is pH. It falls typically in this range between 1 and 14, where a pH less than 7 means we have an acid, a pH greater than 7 indicates to us we have a base. It's important to say that values just typically fall between 1 and 14. It wouldn't be out of bounds for us to encounter a pH less than 1, even a negative pH, or in contrast, a pH greater than 14, maybe even 15. So we're also saying that as the pH values get smaller, how dangerous an acid becomes, its power increases. The smaller the number, the more dangerous the acid becomes. But for bases, on the other hand, it's the larger the number, where 7 is neutral. So as we move further away on either end of the spectrum, away from neutral, how dangerous the chemical becomes also increases. We have something new we've never encountered before, pOH. It's taking everything we know about acids and sort of turning it upside down. For the pOH scale, a pOH below 7 is a base, and a pOH greater than 7 is an acid. Both of them have a few features in common. They're both logarithmic scales. That means that the difference between one value is a power of 10. 3 is a power of 10 stronger than 4. 5 is a power of 10 stronger than 6. 14 is a power of 10 stronger than 13. 10 is a power of 10 stronger than 9. Logarithmic scales is all about these powers of 10. So numbers that are two values apart, 4 and 6, say, whether we're talking about the pH scale or the pOH scale, the lower number is the stronger one, and it's two numbers away, 2 powers of 10. 4 is 100 times stronger than 6. Doesn't matter which two numbers. If we're up here from 9 to 11, 11 is the stronger one. It's 2 powers of 10 away. 11 is 100 times stronger than 9. If we're talking about a difference of 3 numbers, we're talking about 1,000 times. 4 numbers, 10,000 times. In addition, something that's going to be a little bit trickier once we turn to the calculations is for both pH and pOH, only the decimal places are significant. So for example, if we have a pH of 3.25, it only has those 2 decimal places. So at first glance, it might feel like 3.25 has 3 significant digits, but it actually only has 2. The same with a pOH, 12.386, only the decimal places are significant. And this one has 3 decimal places, so it has 3 significant digits. Finally, they have something else in common. There are no units. It's just a pH of 3.25 with no units, or a pOH, no units. Mathematically, there's a few relationships to talk about. The sum of the pH and the pOH together is 14. If we had a neutral substance, 7 plus 7 makes 14. But if we had an acid that was 1 spot away from neutral at 6, then the acid 1 spot away from neutral on the pOH scale would be 8. And 6 plus 8 make 14. If there's decimal places, that doesn't change anything. The 2 of them added together makes an even 14.00. Because it's a logarithmic scale, there is a relationship between the pH and the hydronium ion concentration. The pH is equal to the negative log of the hydronium ion concentration. We're going to have some value in moles per liter for the hydronium ion concentration, it's likely going to be expressed in scientific notation. It's going to be a number less than 1. The pH of the negative log of that hydronium ion concentration will give us the pH. The hydronium ion concentration is equal to 10 to the power of the negative pH. These two formulas are manipulated versions of each other. Instead of only memorizing one formula and manipulating it, here we actually have the manipulations separated out, and we're going to memorize each of them. It's a very analogous thing going on with pOH and hydroxide ions. The pOH is equal to that negative log of the hydroxide ion concentration, where once more, the concentration of those hydroxide ions is going to be in moles per liter. It's going to be some value in scientific notation, less than 1. The hydroxide ion concentration is 10 to the power of the negative pOH. When we look back, we see that they're very similar, those two formulas and these. Okay? The idea being that in the end, if we have one of these four, pH, pOH, hydronium ion concentration, or hydroxide, if we have 1 out of 4, we should be able to calculate the other 3. And I hope that helps.